Okay, in the last lesson we learned about lines, which are very important because there are a lot of natural phenomena which are linear in nature. There's two other functions that we're going to be learning about, one today and one later on. The one later on is called the exponential function, whereas lines look like this, exponential function looks like this, grows very fast. Right now the world is in the midst of a pandemic and everyone is learning about the exponential function. Another way that nature behaves is that many things are cyclical in nature. They're periodic. They happen over and over again. Think of your heartbeat. Anything having to do with the body typically kind of renews itself on a regular basis. We go to sleep every night. The seasons of the earth, the daily rotations of the earth, all sorts of things are cyclical in nature. So we need mathematical functions which also exhibit that cyclical periodic nature to them, and that's what the trigonometric functions are all about. That's why they're so important. So that's what we're going to be discussing today. Trig functions rely on angles, and so we first need to discuss what an angle is and how to measure an angle. So let's take a circle here and a portion of a circle. This will be an angle. We often use Greek letters. I'll use theta to stand for that angle. We have an intuitive notion of what an angle is. If we want to make it bigger, we can extend this down. If we make it twice as big, if the spread goes twice as far as that, if you had this big of a piece of pie, you could make the pie twice as big by extending the angle twice as much. So we need a way to measure that. Back in junior high school and so on, we learned how to do it by breaking the whole circle up, the whole revolution, into 360 parts. We talk about 360 degrees in a complete revolution. And so a 90-degree angle are two perpendicular lines. Why 360? Why 90? What's important about 360? It turns out mathematically nothing is. It more than likely has to do with the fact that the Earth takes roughly 360 days to go around the sun. So it has kind of the natural world as its motivation. The same reason we use base 10, 10 symbols to count is because we happen to have 10 fingers. If we were the Simpsons, we would have base 8. So the point is, we want something which is more mathematical in nature rather than just having to do with some accident of our natural world. And the way we do it is we say, okay, let's let this S stand for the length of the sector of that portion of the circle there, and we'll let R be the length of the radius. Then we notice that if the radius stays the same, but if S increases, then the angle is also going to increase proportionally. So in other words, we can think of this angle as being just the ratio of S over R. As R increases, the angle is going to increase. So that's the definition of an angle in radian measure, S divided by R. It's very simple, but it's counterintuitive, mainly just because people are used to degree measure. But there it is. It's a pure number. This would have units of length, and this would have units of length, and so those units cancel out. So you're just talking about a pure number, and you can deal with it as such. So that's called angular measure in radians. Second thing we want to do is to ask the question, what is pi? Okay, I don't want the value of pi, I want the definition of pi. Okay, when I ask this question of my classes, I often take them out into the parking lot or a field, and I put them in pairs and put one person in the center with a big rope, and then the other person walks around the entire circumference of the circle, and they count the number of steps it takes to go around, and then they count the number of steps it takes to go across. And no matter what length of rope they start with, no matter how large the circle, the ratio of the distance around, which we'll call the circumference, and the diameter, which is the distance across, which we'll call d, that ratio is always the same, c over d. And so that ratio turns out to be a number a little bit larger than 3, and we call it pi. So that's the definition of pi. Since the diameter is twice the radius, we can write this as c divided by 2r, and then multiplying both sides by 2r, we get c is equal to 2 pi r. Remember that when you multiply things, it doesn't matter what order you multiply them. Typically, we write it in this order. No reason you have to. It's just kind of usual, in the same way in which if you're talking about describing a house, you'll say I live in a big white house rather than saying I live in a white big house. There's nothing logically wrong with it. We just typically don't do it. So anyway, so there's the distance all the way around the circle. So now we have that. We ask what's the angle if you do a complete revolution all the way around. So that's easy enough to do. Since we know that the circumference, the distance around, is 2 pi r, and since we're dividing by r, we get that the angle of a complete revolution is going to be just 2 pi. So there we have it. If you go all the way around one complete revolution, it's 2 pi. Very important to know. Okay, so now let's go back to Descartes. And remember what he did. He allowed us to be able to draw circles and things like that on a Cartesian plane, and then to be able to express points along the circle in coordinates. So here we go. See how good of a circle I can draw. Not too bad. And so there's a circle. Let's give the circle radius 1 just to make things as simple as possible. And this is your x-axis, and this is your y-axis. And then we will take the angle, always to be the angle starting at the positive x-axis and moving in the counterclockwise direction, like so. That will be a positive angle. We can also go in the clockwise direction, but we'll designate that as a negative angle. So there's a positive theta. We often use Greek letters for angles, and so there it is. So if this is a unit circle, we know what first of all, we know what these angles are. This angle is 0. This is 2 pi if you go all the way around. If you go halfway around, then that would be pi radians. This would be pi over 2 radians. This would be 3 pi over 2 right there. So there's the complete revolution. And so then we want a way to designate the coordinates of this point right here. Given the fact that this is angle theta, how can we write the coordinates of this point dependent on theta? Obviously, as theta changes, the coordinates of that point is going to change. So right here, the coordinates would be 1, 0. Here it's 0, 1, and so on. What's the way to express it right here? And this is the definition of the cosine and the sine. If you have a circle of radius 1 and this angle is theta, then by definition, the x-coordinate of this point right here is the cosine of theta, and by definition, the y-coordinate is the sine theta. If r were equal to 5 rather than 1, then everything would just blow up, and this would be, coordinates would be 5 times cosine theta and 5 times sine theta. So there's the definition. And as soon as we define it like this, we can see some very important properties involving the sine and the cosine. Let me first remind you of Pythagorean's theorem. Pythagorean's theorem says that if you have a right triangle, and this distance is a, and this length is b, and this is c, then you probably remember it. A squared plus b squared is equal to c squared. And let's just take a quick moment and give a proof of that. It's just a beautiful proof. It's one of the oldest theorems we know about. It goes back to the Pythagoreans, obviously, about 400 or 500 BC, as I recall. And what you do is you just start with a square, and then you put another square inside of it. You choose a point, a certain distance here, and you always go, go to that same point on the next side, like that. And then you have another square. We can call this length A, and we'll call this length B, and then, let's call that length C. So then we just ask the question, what's the area of this big square? Well, one way to get it is this length right here is a plus b. So a plus b quantity squared gives us the area of the whole square. Another way to get the area of the whole square is to first take the area of this small square, which is c squared, and then add to it the area of these four triangles. If I take this one and put them like so, we're going to have A and B here, and we notice it forms a rectangle of area AB, and so you can do the same thing with these two, and so you end up with 2AB. Now remember how to FOIL things? We multiply this out by taking A plus B times A plus B, and you first take the first outer inner last, and you end up with A squared plus 2AB plus B squared. And then over here we still have C squared plus 2AB. And now you may see how to finish it. You get rid of those, and we have A squared plus B squared is equal to C squared. So there's our Pythagorean theorem. So anyway, very good. Let's use that. Whoops. Let's use it right here. If I drop that vertical down, then this length right here is going to be cosine theta, because that's the x distance, and then this distance right here is going to be sine theta, because this y coordinate is sine theta. So I see that cosine theta squared plus sine of theta squared is going to be 1 squared. So what did I just say? Sine of theta squared plus cosine of theta squared is equal to 1 squared, which is 1. Very important property. Maybe the single most important property. Well, I don't know. There are several of them, but very, very important property of sine and cosine. Here's another one. Notice that if I were to draw the negative of theta right here, and draw that down, it's not a very good circle there, negative theta. Then notice that the cosine, this is the cosine of negative theta, sine of negative theta. Notice that the cosine, that is the x-coordinate, of negative theta is exactly the same as the cosine of theta. What did I just say? The cosine of negative theta is the same as the cosine of theta. What kind of function did we say in the previous lesson this is all about? A function that satisfies this is called an even function. And if you look at the sine, what happens to the sine? Here's the sine of theta, here's the sine of negative theta. Notice that one is just the negative of the other. So the sine of negative theta is the opposite of the sine of theta, which recall is what an odd function is. So they're even and odd, both very important properties of the sine and cosine. Finally, notice that there's no reason to have to stop even when I go all the way around. If I thought of this angle right here, that angle would be what? It would be 2 pi, that's one complete revolution, plus theta. And if I go 2 pi plus theta, I'm going to end up at exactly the same point. So the sine of theta plus 2 pi is going to be exactly the same as the sine of theta, because they end up right there. And similarly, get rid of this, the cosine of theta plus 2 pi is going to be equal to the cosine of theta. And we wouldn't even have to stop with 2 pi. We could go 2 pi, go around twice, 4 pi, and so on. So they just keep repeating themselves over and over again, and that's why we call these things periodic functions. Okay, they keep repeating themselves. So we'll talk about that a little bit more right now. Okay, here's what we're going to do. We're going to sketch the graph of sine theta. Okay, sine theta will be the value, theta is the value that goes into the function. Sine theta is going to be the value that comes out. So we'll graph all those points, sketch all those points, see what kind of graph we get. So let's think about it. If theta is 0, which means we're right down here, always remember we're looking at the y-coordinate. The y-coordinate of this point is 0. By the time theta gets to be pi over 2, the y-coordinate of this point is 1. By the time you go all the way around to pi, the y-coordinate of this point is -1. I'm sorry, is back to 0 again. The y-coordinate of this point is -1, and finally the y-coordinate of this point is 0. So what did we say it does? It goes up to 1, back down to 0, down to -1, back to 0, and then if we wanted to, it just started over again. So this is pi, this is 2 pi, this is pi over 2, and this is 3 pi over 2. And it goes up to 1 and down to -1. So, and there's no reason that we have to restrict ourselves to positive angles. We can go negative as well. If we went negative, it would just do the same thing like that again. So there's the graph of the sine function right there. And we see that it's periodic. It just keeps repeating the same thing over and over again. Let's do the same thing with the cosine. Okay, the cosine. Cosine is the x-coordinate. Let's think about the x-coordinate of this point as we go around. It starts at 1. By here, the x-coordinate is 0. Now the x-coordinate is -1, 0, and back to 1 again. What did I say? It started at 1, goes to 0, goes to -1, goes back to 0, and goes to 1 again. And then it just keeps doing that same thing over and over again, just like the sine does. You notice that the shapes are exactly the same, it's just that the one is shifted from the other one. So that's another property of those two functions. So we'll stop here for now, and then we'll go on and look at some other properties of the trig functions in the next lesson.